Thank you very much for the invitation. I'd like to explain a story which is not particularly new. It's now a couple of years old, but my excuse is I haven't actually talked about this, I don't think, on this continent yet. And also there are some new things in the subject, and I think it's still a very rich and interesting subject. Very close related to numerical geometry, not so close related to symmetry, but there's going to be a little bit of physicality in a minute. So the subject is Hilbert schemes of points on very special singular surfaces with tiny and vast singularities. So I'll start a very brief section explaining something about the geometry of Hilbert schemes. A lot of this is just a fixed notation and so on. Then I'll explain something about the topology of these Hilbert schemes, and in particular what's our main conjecture. And then there are two sort of other subjects that come in, combinatorics, very much along the lines of the sorts of things Jim did yesterday for type A. And then, perhaps more interestingly, so just the type A story in itself is not that interesting. It's not without some interest, but as it turns out, actually it was discovered already twice independently by other people. But it's really the representation theory which I regard as a much more interesting part of the story. And in particular, we can make progress on our conjecture, which we couldn't have done just with combinatorics. So that's what I'm hoping to explain. And I'll try to give you an idea of the proof in the type B case in particular, which is the new thing here. So let's just start with the geometry. So X quasi projective variety over the complex numbers. And I certainly don't assume it to be non-singular, but let's assume it to be irreducible and reduced, just to be on the safe side. So then there is the space that I'm going to denote n of x, which is so informally the Hilbert scheme of n points, and formally the moduli space representing the functor, which considers certain subschemes of x, namely those with structure sheaf finite length. So this is as points, it's z. Z x is subscheme, OZ finite length n. So once again, informally, it's n points on my variety, and then they can come together in some kind of interesting way. And without this non-singularity assumption, there is a Hilbert morphism from the Hilbert scheme of n points of x to the n-symmetric product of x, which of course is x n times divided by the symmetric group. And so there is one theorem, which of course is very well known, is that Hilbert of x is smooth for all n. That happens if and only if certainly x has to be smooth, because Hilbert 1 of x is x, and the dimension of x is less than or equal to 2. And of course, the dimension 2 case is the content of the theorem. If in dimension 1, this is an isomorphism, and the symmetric product is already non-singular, and in dimension 2, the symmetric product is singular, and this is a Krappmann resolution. So that's a very well-known story. I don't want to dwell on that. It's not going to be very relevant. There's another theorem which is less known, and part of it is new, and that's certainly, with hindsight at least, we didn't know. I mean, that theorem wasn't around when we started our work, but it very much fits in. Hilbert of x is irreducible for all n in the following cases. So A, this is an ordered result of Altman, Yarobino, Kleiman. So for dimension x equals 1, if and only if x has locally planar singularities, and B, for dimension x is 2, so this is a result of Sudong Zheng, and that's a recent result. If, it's not an if and only if, but certainly if x has rational double points on it. So I'll define rational double points in a minute, but this is an important statement, so you might think irreducibility is a kind of technical thing, but this is very nice and very important. So recall that, of course, if I take n distinct points in the symmetric product, then I get, so there exists, if you want a map from, if I take the symmetric product and I take the, just put a 0 here, so denoting the complement of the discriminant, the complement of where points come together, that embeds into Hilbert. And basically then the statement is that in these cases, this is just a closure of this obvious component in the Hilbert scheme. So another way of saying it is that every cluster, every zero-dimensional subscheme actually deforms to a nice smooth subscheme, namely n points in the smooth locus. So this is a very nice and important statement. I can't quite get from Zheng's paper whether he thinks it's an if and only if. He certainly doesn't prove it, and he gives some examples of singularities, even finite quotient singularities, where this fails. I think he's not quite sure about some classes like minimal elliptic. I think there's some work to be done, but certainly this is good enough for us. So this singles out this set of singularities where you actually have a non-singular derivative. So an irreducible Hilbert scheme, which is kind of nice and pleasant. So another recall is that what's a rational double point, the vast singularity, Kleinian singularity. There are of course many characterizations, but one characterization is that P in X, the surface, is a rational double point if locally, say analytically, it's isomorphic to P in C2 mod gamma, sorry, in G will be C2 mod G, and I'll put a delta here, because that will index my data, so G delta here is a finite subgroup of SL2C, and there are three types, so G delta could be either abelian, so this is called type A, or binary dihedral, this is type D, or exception. E6, 7, 8. And this is, of course, just goes back to the undergraduate classification of finite subgroup of rotation group SO3. Homework for Ezra.
Oh, did you say SL3?
SO3.
No, no.
SO3.
Oh, right, okay.
But the point is, it will be very important for us that this delta here is going to, for me, denote a Dynkin diagram. So there's an associated Dynkin diagram, which is all part of the entire correspondence. But so here, delta is a simply laced Dynkin diagram. And this diagram will play a very important role a little bit later. So I'm just going to index everything. Yes.
So these results almost, but not quite, I could imagine, could have been invariant theory in the 19th century, or is it an entirely different direction?
It's not an entirely different direction. I mean, Zheng's proof is non-trivial, so you have to have some handle on. I mean, his work is sort of pure homological algebra in the style of, I don't know, Mike Weems, and these people are studying these maximal polymodules. So, I mean, it's not quite invariant theory. It's certainly algebra. It's homological algebra. You have to understand these clusters. Matrix factorizations come in, and so on. So there's something to understand. I mean, these are infinite. You know, the singular points here are of infinite homological dimension. You have to somehow have a handle which handles that sort of situation. So no, it's not purely invariant theory. So I mean, the Altman and so on work, of course, is old, but it's not. Again, it's not just. I mean, it's deformation theory. You have to understand the deformations of these clusters. Okay. So of course, this definition doesn't quite explain why are these called rational double points. I'm not going to tell you. There's of course a whole lecture here to be given about what RDPs are and how they relate to this stuff. But given that this definition will be the important one for me, I'm just going to leave it like that. Okay, so just an aside, so what I'm going to say now is not going to be that important. If I write on this board, sort of difficult for you guys over there? Maybe I'll use this. This is just an aside. So there's another set of recent results which looks quite interesting. So, which is for n equals 2, and let's just state the local case. So because of the reducibility of the Hilbert scheme, you can actually prove that Hilb 2 of x to sim 2 of x still has the classical description. It's still of the diagonal. So the whole point is, because you're in a singular situation, you just have to rethink all the results you know about smooth Hilbert schemes and just make sure that they apply. But this particular one can be proved. And so the theorem is, and this is a very recent result of Yamagishi, is that actually this Hilb 2, or indeed sim 2 of x, let's say Hilb 2 of x, admits a symplectic resolution in all cases. Which is not quite, which is close related to, but not quite. Hilb 2 of y, where y C2 mod G delta x is its own minimal resolution. So of course this C2 mod delta, these singularities are well known to admit, these unique minimal resolutions. Hilb 2 of this minimal resolution is certainly somewhere in the picture, but that doesn't quite map here. Hilb is not quite Funter. But it's a few Mukai flops away from it. So you do some Mukai flops on this guy, and you do get a symplectic resolution of Hilb 2 of x. And he in fact says more. This particular singularity appears still in the Szendroi theory as a subregular, transfers to some deeper orbit than the usual one. So the singularity of x occurs in the Szendroi slice, and actually so does the singularity on Hilb 2 of x. So there's some interesting geometry here, which is probably worth exploring further. Which is just being studied. So that's not going to be important for us, but I thought I should mention. Okay, so let me now move to topology. So that's all I wanted to say about the geometry. Any questions? So if not, then I'll start talking a little bit about.
I hope this is not too off topic, but I've been thinking about it ever since you said it. In this first theorem, for dimension 1, irreducible if and only if it's locally planar singularity. So do you know what is the subscheme of the coordinates that does not deform?
I think it's going to be very similar to C3. I mean, because so if your embedding dimension is at least 3, and you have 3-dimensional clusters knocking about, and it's going to be the same kind of stuff as in C3 itself. That's not a proof, and I don't. And to be honest, I'm not with that in paper recently. But it's going to be very similar. As long as you're out in 3 space, then somehow these Grassmannian. I mean, so the classic. I imagine is. I mean, Robino of course had these examples of why Hilb of C3 is irreducible, and I can't imagine that this is going to be a million miles away from that. I mean, you just write out these deforming clusters on C3 and impose the equations, and there'll be something left. I think that might be the. I mean, that's a very common. So for example, the proof of this is very similar. You know this result for C3. You embed x into C3, and you use the irreducibility. So that's kind of the theme here, that your embedding dimension somehow drives the cluster. So let's look at it, but that's kind of the idea. Okay, so topology. So for today, I'm going to take this very crude measure of topology. So I want to consider the partition function. Everybody's, a lot of us, favorite function. I take the generating function let's say 1 plus generating function m greater than 0 of the just topological Euler characteristic of f of x q to the n. So that's one very crude measure of the topology. I just brutally take the topological Euler characteristic and I see whether this function is interesting. And the sort of comment that applies to this function is the same sort of comment that applies to Jim's function. That quite why we're doing it initially is maybe not so clear, but these are nice states, nice functions. And, certainly some, although not everything, I would say, has extensions to things like concrete polynomial or motives or whatever. You can try and soup it up. Some of the results have known generalizations like that, some don't, and obviously are asking for it. Okay, so of course, in dimension 1, x plus singular, then zx of q is 1 minus q is a minus the Euler characteristic of x, and this is just a generating function for the symmetric product. So that's not so very interesting. Dimension x2, x non singular, then of course we have specialization of the Bircher formula, E of q to the Euler characteristic of x. So what is E of q? E of q is a product, it's the Euler product, 1 minus q to the n inverse. So this is of course Lothar. So the next case, if think about the geometric results, the next interesting case is planar singularities, and some of the culprits are in the room, of course. So the theorem here, so is as a conjecture, this is due to Ogonko and Szendroi, and it was proved by Maulik a couple of years ago. So this deals with this dimension 1 case. So if dimension of x is 1, x has locally planar singularities, then there's a very beautiful formula which says zx of q. So the same thing as you had before, 1 minus q to the minus the Euler characteristic of c. And then there are local terms. So the fact that there are local terms, that's not in itself very difficult. The question is, what are the local terms? So this product goes over the singular points of x. And the formula is something like q to the half over a to the mu I. I'll explain this in a minute. P li q to the half a. Take that whole thing and evaluate it at 0. Okay, so I have to say what's the mu I and what's the li. And what's the p?
So does locally planar singularities just mean that x locally has planar singularities, or?
Yes, so locally the embedding dimension is 2.
Okay.
Doesn't, I mean, it's locally a plane curve, but it doesn't have to be globally a plane curve.
Okay.
So there is cotangent space at every point is 2. Okay, so where locally, of course, we have pi contained in my curve, and that's contained in C2. That's the assumption locally analytically. So mu I is the Milnor number of the singularity pi in x. Li is the link. I intersect x with a small ball inside C2 centered at pi. So this is a small free ball centered at pi in complex 2 space. I intersect that with the curve itself. That's a one-dimensional thing. That's a link, and then p li q to the half a is function of this link. So this was very exciting when it came out, and then also the proof is quite beautiful, and there it is. So I don't want to say much more about it. So this somehow suggests that in the two-dimensional case, sorry, in the one-dimensional case, the subject is in topology. What it relates to is, in the first instance at least, is these Humphrey polynomials of links. Of course, it has other very deep relations to representation theory, but that's very different from what I want to say. So what we want to do basically is, so our project started by kind of taking the fiber product in the obvious diagram. You have non-singular curves going to singular curves, you have non-singular surfaces. So it's clear what you need to do. Something about singular surfaces, and in particular then a very natural class, and certainly in light of these results, a very natural class is rational double points. So I should say we were the only ones to study this, but we were the first one to solve it. Right, or at least conjecturally solve it. So what is our conjecture? So let's go back to then the surface setup. So for the rest of the talk, X is going to be C2 mod G delta. And I should say, once again, the Hilbert scheme has this very well-known stratification. So the fact that there is a formula like that, which basically takes a smooth answer and local corrections, that in itself is not deep. It's basically very standard. The question is, can you understand the local corrections? So I'm just going to restrict to this local case. And then everything else will have the same form. So for a general surface with singularities of this type, up to analytic isomorphism, there will be a similar product formula. So all we need to understand is Zx of Q in this case. And then everything will package together into a product. So here's our main conjecture. So I wrote, but I didn't say that all of this is joint work, so I'll write the names again. So Adam Jenge is with Jim at the moment, he was here last week, and András Németi in Budapest. So we conjecturally answer this question. So the following is our formula. So we have EQ to the r plus 1. I'm going to explain all these terms times the sum m in lambda r, which I'm going to r lag, which I'm going to make isomorphic to zr, zeta m times 1 q to the half m, where so r is the rank, is the number of nodes in the Dynkin diagram. So delta is a simply laced Dynkin diagram. It's ADE, it's got some number of nodes. That's the r. Notice r plus 1 here, that's important. And then lambda r is the corresponding root lattice. With basis simple roots. So I make a choice of, if you want, choice of simple roots, so I want to make it isomorphic so that I can write this. But the main thing is here, which is that what we are using here is the inner product on the root lattice. And psi, that's also an important part of the story, exponential 2 pi I 1 plus Coxeter number. Actually, maybe it's more than show to our real Coxeter number, but it doesn't matter. So some root of unity. So H is the Coxeter number corresponding to the root system. Okay, so that's our conjecture.
What's one underline?
It's just some of the amount in this. One underline, 1, 1, 1.
Oh.
This is just a shorthand for some of the amount.
Is there some way we're supposed to see why this doesn't have any fractional powers of Q in it?
Oh, that's an even. It's an even. So that's an even. That's fine. That's about the only obvious part of this one. So, for example, one other thing
It's always the same root. Sorry.
One other thing you're supposed to see here, which is less obvious, is why are these integers, for example, which is less obvious. Okay, so that's our conjecture, and I'll tell you where we came from. But just to give away the punchline, the theorem is that the conjecture is true for delta of type A and D. And okay, maybe I should do this one final time. So everything I'm going to say is with theorems. Okay, so I'll stop writing collaborators because everything from now on is the three of us. So we can prove it in the two infinite cases, and it leaves only the three. Of course, probably the most interesting cases. So we can we're a bit short of a proof, and I should say right away that our proof is very type dependent. So it's a case by case thing. So I'll come back to this. Of course, this sort of conjecture really is out begging for a uniform proof. And so for the rest of the talk, I'll say where this conjecture comes from, and I'll interpret it in different ways. So you're not yet supposed to fully understand it. I don't fully understand that. Okay, so where does this come from, and what can you do here? So this is section 3, combinatorics. So in type A, everything is nice and easy. So let delta be of type A. Or, so linking diagram. So G delta is generated by omega 0, 0 omega inverse, where omega is exponential 2 pi I over r plus 1. And just to sort of give a, so h check is r plus 1. So this root of unity is not the one expect. It's exponential 2 pi I over r plus. So there's a shift in the root of unity. So the group is generated by one root of unity, and then this substitution, or this root of unity that comes up in the formula is 1. Shifted. Okay. So the reason this is nice and easy, of course, is that this is an abelian group, and it commutes to the full torus. So of course C2 has an action of T, which is C star squared. So this is really identical, or very, very close related to the sorts of things that Jim was doing in his talk. So T and G delta commute, because G delta is just a diagonal group, and so T acts essentially on everything inside. So in particular acts on these Hilbert schemes of X. So that's very nice. So just recall, maybe as well as Hilbert of C2, so the thing upstairs. So that's very nice. So recall that the torus fixed points just on Hilbert C2, P, these are just in one-to-one correspondence with partitions of N. So this is very well known, not used by lots of people in this room. And the idea is just that when you have a partition, then there is a you think of a partition as occupying spots in the xy lattice, and then so 1, 2, 0, 1, 2, 3, 4, 5. So there's x to the 6 here, x to the 4, y squared here, and y cubed here. So that little picture corresponds to an ideal of a cluster generated by these monomials. So maybe I should also say that this also corresponds to ideals of CXY that are monomial. And those correspond according to the picture. Okay, so this is well known. So now what you need to understand is just what happens to this picture when you put in the finite group. So when you put in the finite group, then so you have to do this essentially equivariantly. So this G delta, which is of course isomorphic to a cyclic group of order r plus 1, X here, it has characters rho I mapping the generator to omega to the I. These are the one-dimensional characters of this group, and these characters will color or label or whatever label the lattice as follows. So I'm going to draw the same lattice, xy. So you can imagine your monomials. And instead of writing the rows, I just put, in some color, I put the numbers. So here, this monomial is monomial 1, and that's in the 0 character space. That is invariant under the group action. This is xy. So the whole point about it, we are in the special linear group, so determinant is 1. So this entire diagonal will be labeled 0. Do people understand what this labeling means? So here there's a one-dimensional, I'm basically decomposing cxy into isotypical components for the characters. So this is 1, so the way I labeled my group, so x gets multiplied by omega, that's the character 1. So this gets labeled by 1. And then there's r plus 1 characters, so this last one gets labeled, so y gets labeled by r, or minus 1 is the same thing. R minus 1, and so on. And this is a periodic coloring. So at some point, we go up to r here, and then we are 0 again. Okay? So, yes. So that's correct.
Oh, so for r equals 1, for SL2 it's just the usual chessboard.
Yeah, SL2 is just, sorry, SL2 is just the usual chessboard.
Okay.
Exactly. For SL2 you get a chessboard, and for higher you get this sort of diagonally colored space. So here we just label the lattice. And so let me just write down the fact, which needs a little bit of thought, but really not very much. So what was the statement? So the fact is, if I look at now the Hilbert scheme of this x, so C2 mod gamma, let's take the nth Hilbert scheme, torus invariant points, that's in one-to-one correspondence with, I'm going to call 0 generated partitions lambda with 0 weight n. So this is quite easy. So what's a 0 generated partition? So a 0 generated partition should really be 0 co-generated, but that was too clumsy. Basically what I want is just that the things generating it should all be in weight space 0. So should be generated by invariant monomials. Invariant under the group action. And it's pretty clear to see that you want something like this. So here is a 0 generated monomial, and if there's another 0 up here, that's another 0 generated monomial. So that would, for example, be an example of a 0 generated partition. So all I want is that it is generated by invariant elements. And that's more or less obvious, because you want ideals of, well, what is the ring of X? The ring of X is just invariant ring. I can now lift it to that the ideal it generates, and that will be generated by invariant elements. That's pretty much it. There's not much to it. And what's the 0 weight? The 0 weight is, I have to count the zeros inside. So the 0 weights here would be coming from counting the zeros inside, because those are actually elements of the invariant ring. So this is very, very close related to the standard story. Okay, so what do we get? So we get then this definition. So inside, I'm not going to write the formal definition, but inside P, which is a set of all partitions, using this r plus 1 labeling. So it's very important, I won't put it in the notation, but its labeling, of course, depends, this definition of what's a 0 generated thing depends on the R very strongly. Get this sort of set P0 inside P of 0 generated partitions. So that is not a formal definition, but you get a definition, which is just counting, just enumerating these things. Okay, so Now, of course, your business as far as type A is concerned, because there's a finite set of fixed points on this scheme, and there's this very general result, checked very carefully is in the literature for singular schemes as well, is that the topological Euler characteristic in this case is just a number of fixed points. So the get Z delta of Q would be a very similar looking combinatorial sum to the one you're used to, so lambda in P0, Q to the weight C. That's it. Okay, so this is a combinatorial series. You have to solve this combinatorial problem. And in fact, so this implies, so corollary if you want, conjecture is true in type A. In other words, this combinatorial problem can be solved. And in this combinatorial language, this is actually due to digraph Szydłowski. Now, I can't remember, a good 10 to 12 years ago. And we give another proof, and that's actually also quite interesting. So, Lagrave and Szydłowski, they didn't talk about Hilbert schemes, but they were very clearly motivated by very similar ideas. They just wrote down a combinatorial problem, and they solved it using a classical method of Andrew's stuff on partitions. Our proof is different, and I'll come back to what our proof is, and we think it's better because it generalizes more easily. So their work is very closely tied to Andrew's work on partitions, so it's hard to see how that generalizes. I should say this corollary was also, the conjecture in type A was also proved by Toda by completely different methods, nothing to do with this stuff. Toda also showed the formula using wall crossing in DT3. So he has a very, very different proof, and he got to the same formula. So this is where Adam himself, at the beginning of his PhD, he reproved this independently. Was very disappointed when I told him that it's already in the literature. But of course, his proof was better because we could generalize it, a lot of things. His proof was.
Sorry, how hard was it to get from that formula to the original thing you wrote down in the conjecture with the A?
Yeah, so I mean, it takes some work. It's so when you write that stuff out, it becomes things. So this m.1 and the inner product, these are well known to show up in this work on cores and quotients of partitions. So you have to think about cores and quotients, but you have to think a bit more. So there is some work. There is some work. So in the digraph-Szydłowski method, that's sort of implicit because they really sort of tweak the Andrews method in some way, which I don't find particularly transparent. I mean, they get a nice proof. But whereas in our work, it very closely relates, and I'll come back to that point. It very closely relates to the enumeration of all colored partitions.
Oh.
And then actually, then you have to translate the cores and quotients into this thing called the Mie diagram. And in the Mie diagram, it becomes combinatorics, but it's still a page or two. So it's not
diagram?
Mie diagram. So that's this thing. I won't do Mie diagram. I'll spare you Mie diagrams. But it's actually a very beautiful combinatorial method to deal with partitions.
Just to, I mean, I'm looking at it and guessing that you're looking at partitions where all the parts are congruent to one mod R and all, the conjugate the same. Is that not? It's not. That's not the right condition.
No, it's really. This is So. What to say? I'll come back to the representation theory. Let me not give away the representation theory punchline. The combinatorics, it's not a punchline, but it's certainly a line, is that once you translate this into the Mie diagram, which I won't, then these become very natural operations. And there is, in fact, there's a kind of obvious map backwards. You can take any partition, you can take, there's actually two maps, a map and a co-map. You can take the largest zero generated that's contained it. That contains it, and the smallest zero generated contained in it, and so on. And all these things have very natural representations on the Mie diagram, but it's not as simple as what you say. I mean, these are all slightly different. But I mean, the short is, this has a proof and it's representation theory. And from that point of view, that you can sort of see that root of unity. In fact, okay, let me say this much. There is a map backwards. For any partition, you can take, I can't remember which is the natural one, but you can take the completion. If you want, you can take any ideal and you can intersect it. That's one map. And basically what that substitution does is you take the generating function of all partitions and you ping in that substitution, and somehow magically that picks up exactly, it sort of sums and integrates along the fiber of that map somehow. And that combinatorial substitution knocks out everything except the one guy that you're actually interested in. So that's the flavor of the argument.
Is this also, are these formulas a specialization of the counting function for the Hilbert scheme of points on the orbital?
Yeah, I'll come to that, yeah.
Okay.
Of course, you're cheating, it's the story.
Well,
Right. Okay, so that's type A. Let me leave type A at that for now. I'll make a couple of comments. Just a little bit later. So it can be done and it can be brought into that form. And that was so the starting point of all the rest of the work is there were sort of two starting points. One was that, of course, this is a picture that representation theorists know very well and is very intimately related to the basic representation of the F-9 Lie algebra. That was the one starting point, and the other one was that after some work we saw that the conjecture can be formulated in the way I already presented it to you, which is completely Lie theoretic. There's nothing in there about partitions or all the terms in the conjecture, which unfortunately deleted, is purely Lie theoretic. So it had the root lattice, it had the simple roots, it had the rank, and it had the Coxeter numbers. So there's nothing in there that you can't at least say for all the other types, and then of course you want to prove it. So actually let me come to the point Jim has just made, which is that you can write down a bigger partition function. So if you take any representation of G delta, not necessarily irreducible, then you can define the row Hilbert schemes of C2, or if you want the Hilbert schemes of the stack, C2 mod group. So in a kind of pedestrian language, these are ideals which are G delta invariant, so that if I take Cxy modulo I, then that's G delta isomorphic to rho. And then this was an observation made a long time ago, perhaps by Brown and Massaro, perhaps even earlier, is that if you take the Hilbert scheme, the whole Hilbert scheme of C2 mod C2, and you take, basically do what I just said, take the invariant ideals, that decomposes exactly into these things, more or less tautological. So this is an almost tautological statement. The only thing that's not tautological about it is that because these are non-singular and this is a finite group, these are also non-singular quasi-projective varieties. That's, of course, important. These are non-singular. And then you can sort of take this much bigger generating function, which is which we call the generating function of the orbifold, with some variables q. So there is now many variables, one for each node of the Dinkin diagram. So q is q naught to qr. And I'm going to take the sum over all representations of the topological Euler characteristic of this Hilbert scheme, Hilbert C2, and q to the rho. Where what do I mean by q to the rho? So here rho is some Li rho I goes from 0 to n, and q to the rho is just a product of qi. Okay? It's a simple thing, so everything is a sum of the decomposables, irreducibles, and you get that. Okay, so this is a much bigger sort of master function. And what can we say about that? Okay, so theorem, and this really is a theorem, and this is in all types, which is, of course, where conjecture very closely relates to our conjecture, is that this is known. So that C2 G delta of Q is, okay, so E of Q R plus 1. So here the straight Q is Q to the delta. So delta is this Dinkin indices. If you want, the delta is just the dimension vectors of the irreducible representations.
So it's the regular representation.
It's regular. It's the regular. Yeah, it's a regular representation. So that's the Q, and then sum, same thing. So M over the root lattice. Once again, I've chosen it to be isomorphic to R with some choice of simple roots, and then the formula is product dy to the mi, and goes from 1 to R. So these are the Q's, not all the Q's, just the Q's corresponding to the finite finite roots, or in the language of representations, non-trivial representations, times Q to the half. So that's the single Q, that's the same Q there.
Oh yeah.
Okay, so where does that come from? So this is actually what's the cardinal? Decategorification. It's a decategorification of the following theorem. And this is essentially Hiracou's result. I'm not sure he ever stated it in precisely this form, but it's the following. If I actually take the homology of all these guys, Hilbert C2, throw in the representations of G delta. That's isomorphic to. Okay, so I'm going to write F tensor and I'll just explain lambda 0. So what's going on here? So F is Fock space. So this is one copy of just a rank 1 Fock space. So this V lambda 0, this is a representation. This is the basic representation, basic level 1 representation of the affine Lie algebra corresponding to delta. Okay, so let me not explain this. This is, again, not explain this fully. But what goes into this statement are the following, in fact, as G hat, and then there's a little extension representation. So what's G hat X? That's basically direct sum of G with a Heisenberg line. Modulo sum one-dimensional thing. Okay, so this is a lot to parse, and I won't be able to explain this fully. But the first point is these are Nakajima-Kuro varieties for the corresponding affine diagram. So that's well known, and that's very much part of this work. Well known after essentially Kronheim and Nakajima. They don't have cohomology, that's proved somewhere in Hiracou's work. And if you take the total cohomology that has actions by correspondences of essentially the affine Lie algebra, and then also if you put in correspondences which move around the cohomology, then you get this extra Fock space. So that's the theorem which is due to him. And the point is now, this is a very well-known thing here. And if you take the character, you recover this statement. So basically all you need to do is on this side you take Euler characteristics, you get this generating function on the nose. And if you take the character, Q character on this side, then one copy of this EQ is responsible for this Fock space, and then the rest of the formula is the Frankel-Katz construction of the basic level 1 representation. So somehow this is not surprising. It's surprising from our point of view somewhat. So in particular, then, for type A, this gives the generating function of all colored partitions. And that's important. So in type A, all you're doing with this stuff, and again, I won't explain this fully, but that's not difficult, and it's purely combinatorial, is to say what are the torus fixed points on this equivariant Hilbert scheme. And they are precisely they precisely correspond to colored partitions. So maybe I just put this in a remark. In type A, this is just the generating function of all colored partitions, or if I call them label partition. And it does have its independent proof. So of course, to prove this statement for type A, you don't need any of this representation theory stuff. You can just write down, you can just sort of follow the same kind of argument as we use for the invariant Hilbert scheme, for Hilbert scheme of the quotient, for the Hilbert scheme of these stacky things. There's a one-to-one correspondence with labeled partitions, you get a combinatorial sum, and then you go into literature, go to literature, and discourse and quotients and Murray diagram and whatnot stuff proves precisely this formula in type A, completely combinatorial. So once again, in type A, you can view this project in type A as purely combinatorial, but the whole point is it's not just purely combinatorial, there's all this representation theory behind it. Okay, so that now, of course, exactly as Jim says, that now gives a handle on the conjecture of sorts. Because what you notice, or of course that was more or less how we wrote down the formula, my conjecture ZXQ is just a specialization. The conjecture, I should add at this point, this is the conjecture ZXQ is just a specialization of this much bigger thing, this stacky thing, specialized to Q equals Q, just keep the Q, and then the finite Q's you put to the root of U. And that's somehow remarkable and certainly not fully understood. So in type A, as I sort of more or less said, that this is what's going on. So you take the full partition function, you substitute these roots of unity, and it picks out these zero generated partitions. So that is a combinatorial fact, and that's that. But there is more going on, because this substitution certainly makes formal sense away from type A, and in fact it makes actual sense as well. And this now certainly guides us as to what needs doing. So in the last 5 or 6 minutes, let me just say what we do in type D, and all I want to do is draw a picture, state one theorem, and then just wave my hands for the rest. Yeah.
Is the right-hand side integer valued as a power series for all types?
Okay, yes it is. So the two things. Experimentally it is for E6078, and I think Ettinghoff explained the proof which proves it that it's integer valued. But I haven't written down the details. So that's a good question. But yes, certainly it is experimentally for a very large. Yes. So the answer is yes. But it's not obvious. Okay, so what do we do in type D? So type D it starts as a very nice story again. And so basically you have to take everything and that you did in type A and translate it. And of course you immediately hit a stumbling block. So what is the group? So G delta is now of course not diagonal. It's generated by the same sort of thing, along with 0, 1, minus 1, 0. And I don't want to commit myself to what the root of unity is compared to the m, at m plus 2 or m minus 2, I never quite remember, but it's generated by this sort of root of unity and essentially the dihedral deflection, x goes to y, with a twist to make it SL, and then it doesn't commute with the full torus. So it commutes with diagonal C star only. So this is of course a very well-known headache that if you want to take anything in type A and translate it to type D, you immediately are hit with the fact that you have a much smaller symmetry. And of course that implies that all you can reduce to is, you can take torus fixed points, C star fixed points, but that's not at all an isolated set. It reduces you to homogeneous ideals, which is useful, but they have moduli, of course. And this came up in Hilbert's talk last week. I mean, whenever you move from type A to type D, you lose the finiteness of fixed point sets inside. So you somehow have to handle that. So that's one problem, and of course the whole story is a lot more complicated. So what can you save? And one thing that can be saved, and that's absolutely key to our approach, is that there is an analog of P. So how should we see P? So I sort of didn't say it, but it's implicit in what I've said, is the role of P in this isomorphism is it gives you a distinguished basis of the right-hand side. So P, crystal basis of F tensor P lambda naught. So once again, that's another subject that I know little about. The little I know is that you can find it in the book. The point about crystal bases is that these representations of affine algebras, as these deform to the quantum group, and then there are distinguished bases in them, distinguished sort of positive bases in them, which somehow behave well with respect to the quantum parameter going to 0. That's more or less my level of understanding. But it's somehow key in the theory that these distinguished positive Lustig Kashiwara type bases exist. And we sort of treat this, I mean, nothing that we do is explicitly representation theoretic. We can do everything we do without invoking representation theory. But this is a point that would have been completely lost without looking in the literature and see what is the type D crystal basis. Because otherwise, we couldn't have made any progress. So somehow, this was perhaps a key point of the project to reinterpret this set of partitions as the crystal basis of this representation. So once again, in type A, this is very well known, and it's not a surprise. But what is perhaps surprising is that the same approach extends to type D. So I promised a picture. So let me do the picture now. And the picture is nice. We were lucky also that the type D crystal theory has been developed by other people in this language. So, sorry, this is a bad moment. Kong and collaborators. So a group in at the University of Seoul, Kong of course wrote a big book on crystal bases. There's some works that have developed the crystal theory for type D in analogy B. So I should say there's nothing unique to crystal bases, and whoever works in crystal bases, there is some paper in the literature called uncountably many crystal bases for the basic representation. So somehow there's nothing, although a crystal basis theory is very useful and very nice, there's nothing kind of got sanctioned about what crystal basis and what combinatorial model of crystal basis you choose. But it turns out that for type A, partition is a very good one, and there was an analog theory in type D already developed. And but I say we would have had much harder time if we had to discover that theory. But it is possible to discover it from this picture. So I'm just going to give you a picture, a theorem, and then conclude that. So what's the picture? So I'm going to draw the same picture as before, the xy lattice. So we're still working in the xy lattice. And look at the group. It's got the affine part, the type A part, so just these matrices, but then also this diagonal matrices, but also this dihedral symmetry. And the dihedral symmetry basically does this to this picture. It just interchanges x and y. And so what tells you to do right away is to draw, I hope, let's start it. Let's start it here. Anyway, the top half will not matter. So basically you can ignore the top half of this picture. So you can just ignore this. Okay, so that's your first move. You ignore the top half of the picture because representation theoretically that doesn't matter. That's a symmetry. So what is also recall the Dinkin diagram. So this is, I just do this for D4. So this is the Dinkin diagram. There is kind of the special vertex corresponding to the trivial representation. And then, of course, the rest of the D4 Dinkin diagram. So there is one representation, which is the sign representation. There is a two-dimensional representation in the middle, and then row 3 and row 4. So this is isomorphic to actually C2, the given representation. So that's the picture. And you can label this picture just as before. So this is the trivial representation. This gets labeled 0. This gets labeled 1. xy is the sign representation, if you think xy just goes to minus xy. X squared y squared is an invariant. So here you just get this pattern. Okay, so here, this is x. It's a representation together with this mirror image. It's an irreducible representation. This splits into 3 and 4. X squared and y squared individually are not invariants, but they are, together with the mirror pair, they decompose into x squared plus y squared, x squared minus y squared, or maybe there's an I in there, I can't remember, which gives you these one-dimensional representations, the ones at the outer bits, outer space in the universe. And then this goes back to 2, this is a 2, this is a 2, these are 2s as well, so it's a sort of related diagonal coloring, but you get these split boxes. I think we made this split on the other way around. Just did it this way, but somehow what's important is I mean, the details will not be very important. But what is also important is that as you move up, you multiply by x times y, and that flips 3 to 4, 4 to 3 in some specific way. When you go back here, this is x4 plus y to the 4, and that has a trivial and a sign component. So that continues. And then that's 2, that's 3, 4, 2. Okay, so that's the picture. Can I take 3 more minutes to check?
Yep.
Thank you. So this is just once again the picture of the xy plane decomposed into reducible representations of your finite group. Now you open these books or papers of Kangen people, and they define a type D crystal basis as some kind of finite subset of this configuration, a kind of partition-like subset. They insist, because they don't come from the Mackay correspondence, they insist on drawing this into a rectangle rather than a quarter plane rather than an octave, which I think is more natural. And in fact, the rules are more natural if you draw it like that, but it doesn't matter. So meditating over this picture gives you a thing we call type D partitions or type D crystal bases. Type D and crystals or partitions, certain finite subsets of this diagram. So this is somehow the key diagram. But amazingly, if you meditate over this in Lie theory and if you meditate this over the Mackay correspondence, you get to these very complementary but completely fitting kind of thoughts. Okay, so let me just conclude with 2 formulae. This unfortunately hides a huge amount of, by and large, quite technical. So here's the first theorem, which is kind of a geometric version of this result of Nakajima, is that there exists a stratification. So I take all these field rows. This is type D, disjoint union over all row. That's sort of equal to the disjoint union over all lambda in the type Dn crystal basis, some strata, y lambda, with y lambda isomorphic to affine space of some dimension, depending on lambda. So that's the first geometric statement. And if you see, that's a categorification of this. So what we're saying is that actually these spaces have affine pavings by affine pieces. So what is that cohomology? That cohomology is just a one-dimensional generator in the right degree. And maybe I should be doing, I always forget whether this is what sort of cohomology this is. Let me sort of skate over that point. And the point is, I'm just basically understanding this representation dimensional sort of piece by piece in its basis. So on the right-hand side, if you take the generating function, I basically get the generating function of these type T partitions, which of course is giving me that formula up there. So this is a geometric statement. Our approach is inductive, and these numbers are unknown. Of course, unknown to us, because we are lazy. If you go anywhere near the paper, you'll see why we are lazy. This point gets in about page 51. I mean, somehow I'm advertising the subject here. I'm advertising the theorem. I'm not advertising the proof. So let me just write down the other theorem, and I then conclude. There exists a combinatorial subset P0 dn inside Pdn, such that the partition function we are interested in, that x of q, is just, it's the same formula, q to the weight 0, that's called lambda in P0 dn. So this is a weaker statement. Underlying this sort of statement is a sort of stratification of the invariant Hilbert scheme, but that's, at least we can't prove that it's by affine spaces. But anyway, we can compute enough about the Euler characteristics that we get to this point. And once you get to this point, then you say, okay, the rest is combinatorics. And that is true in our approach, it's another 20 pages of combinatorics, I'm afraid. So once again, I'm not here to sell the proofs, but if you put the ideas, the geometric ideas together with this statement and the combinatorial results that we are able to derive, you get a proof in type D. Okay, thank you.
Questions or comments?
Maybe this is buried in the last comment you made, but this suggests, can you get the full point array polynomial?
Yeah, right. I mean, if you computed the d lambdas, you should. Okay, so two things here. One is, can you compute these d lambdas? And I think the answer is yes. And even from a close reading of our paper, there is certain information in there. We do an inductive proof where we prove that certain things certain maps between Grassmannians are affine fibrations, and some sort of maps are pulled back from them. I mean, the short answer is probably yes, but the slightly longer answer is d lambda is likely to be some kind of complicated statistic of your partition, and you still have a combinatorial problem to prove. But yes, I mean, in general, you could I mean, these are nice varieties. You should get the motive, right? I mean, these are nice basic projective smooth varieties affinely paged. So you should have a nice formula for the motive. We haven't done it. That should be doable.
But you said the singular guy is not affine paged?
Well, we don't prove it. It could be. I mean, in the examples we looked at, it is, but that seems much harder to prove from our approach, which is already pretty crazy. So unfortunately, there is a kind of very complicated inclusion and exclusion going on, where you're taking pieces, put pieces back in, taking pieces, put pieces back in. So what is the issue? The issue is, in type A, I drew that picture. You draw the picture, and basically your generators of your ideal are sitting in the obvious boxes. And that's not the case here. So maybe I'm just allowed to make one final time this joke. So somehow, of course, generically, I mean, this is a slightly misleading example. If you do some big Dn, there's going to be lots of things in the middle. There'll be lots of these uniform rows, uniform diagonals that work very beautifully, and that's fine. The thing that gives you the headache is these things. And so these things are like hanging chats. So in the sort of Bush versus Gore election. So they kind of mess you up. They're hanging there, and they sometimes can fly up a little bit. And so basically, when I have certain finite subsets, to define these finite subsets already, somehow in the generic part, which, let's say, for type D, Dn is very small, but for large type D, that would be most of it, is just like a partition type rule. But then there's some very specific rules for these hanging charts. And that messes you up, and that then comes back to bite you. And you can't quite pin down generators of an ideal. That's the issue. That you get a picture, and you would like to say the generators of my ideal are in here, 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 and here. And that's not quite true. They can degenerate, and they can degenerate in inductively quite complicated ways. So all we can say for the singular one is some kind of cookery.
But that does sound perfect for a motivic cut and paste approach, some principle including.
Right. I referred to my paper. It's just a nightmare. I mean, yeah, I can't. I mean, somehow this is the frustrating bit in this project. That I hope the theorems are so quite handsome. I mean, they're kind of nice, and it fits into nice frameworks. But when you go sit down and try and prove it for type D, it's an absolute nightmare. And so yes, of course, but good luck.
Just to be provocative, this is what I thought Jim would ask. What about further refinement states the elliptic genus? Do you have any guess?
I really haven't studied that. I've never in my life written down them.
But these guys are not smooth, though, right?
Yeah, so the singular ones, I don't know. I mean, somehow the equivariant ones we are treating as a tool. So I think for this kind of thing, everything should be, these are very nice, smooth varieties, fit into lots of different pictures, and perhaps it's already in the literature, I don't know. I mean, Leafy General, Nakajima, right? I don't know, I haven't looked at it, I haven't studied that subject, but I don't know. If the point here is you can prove things about the singular guys as well. That's our point, that's the new work, and those are fairly singular things. To give away some kind of thing that I want to study later, I mean, they may still be pure varieties for degenerate stability conditions, I'd love that. That would fit into this framework very well, and that would open up a whole new set of methods to study them. What we can't do at the moment. It's certainly a very obvious conjecture to make that they should be pure varieties for degenerate stability conditions, but we can't prove.
Is there some reason Toda's proof doesn't generalize?
Yeah, so Toda's proof is also interesting. So Toda's proof is completely different. He's never seen the correction to representation theory. He just does the formula. No, there's no reason in theory. All he does is there's a kind of nice float where on the one side of the float there's a surface with this type A singularity, on the other side is a non-singular surface sitting inside a smooth threefold, and he just chases the wall crossing formula. But already, for type A, our proof is 2 pages, and his proof is, okay, he's told us, so it's not 25, but it's sort of 10. So it's non-trivial, as always in this subject, to actually chase the Walker-Ruskin term. So I think he tried for type B, it's an obvious thing to try, and I think he still gave up. And if Toda gives up, that's
Is there a geometrical interpretation to this restriction that you're taking, setting all those Q's associated to non-trivial nodes to the same root of unity?
No, so I have some understanding of this representation theory, but not at all in geometry. And it's bizarre.
Do you expect connection to 3 manifold invariants? So you have a link of
Yes,
this?
yes. That's of course where Nirvana started. And no, so okay, I didn't say, okay, the bullshit line is these are all modular forms. They're modular forms because this is some kind of Jacobi deformation of a theta function. When you substitute roots of unity, you get some function of Q, and you can prove, Toda proved that if you know that you substitute roots of unity into something which is like that, which is modular, and you get integer coefficients, then there is some Gola theory argument that it's actually a sum of theta functions. Therefore, it's modular. So all these things are modular. You're checking a new case of the S-duality conjecture. Now, how it relates to your question is, I've looked through the literature for modular things in 3 manifold invariants, and I've asked Garofagidis and other people, and it just seems a very, very different subject. Most of the theories that they get are very far from being modular. So, no. I mean, that's where the whole project started, of course, obviously, looking at the kind of stuff that Alexei and Vivek did and so on, that was the obvious guess that it should. So what's important here is that the embedding doesn't give you any extra information in that dimension. So 3 manifolds in 3 manifolds in S5, there is no obstruction to moving them apart. There's no knot theory, I think. So all you have is the length space. So the embedding doesn't give you any extra information. So yes, I mean, you sort of suggested that already. All you're looking for is a 3 manifold invariant. Is this kind of thing a known 3 manifold invariant of a length space? And the answer is not to. And not to.
That's a surrogate. I think his whole deal now is he's hunting around people to try to give him modular interpretations of his 3 manifold invariants, and he's got a bunch of examples when he comes back.
Okay, I mean, yeah. I mean, I think Sergei is certainly vaguely aware of this, so I think if that was an obvious answer, he would have already written it down.
Okay, let's thank Balázs again.